This is the Discovery Files podcast from the U.S. National Science Foundation. At the frontiers of astrophysics, new and advanced technologies are necessary to understand the complicated, high-energy, fast bursts of light occurring at the most extreme conditions in the universe. Our guest today is Franklin Dollar, Professor of Physics and Astronomy and Associate Dean of Graduate Studies in the School of Physical Sciences at University of California, Irvine, who works with lasers to understand how high-intensity light interacts with matter. Professor Dollar, thank you for joining us again. I'd like to start with a real general overview question. What is a laser?
So you can think of a laser as a sort of light photocopier. So one ray of light will come in and you'll get two rays of light that come out in a way that makes it almost a perfect copy of itself. And we normally maybe don't think of light like that. I might have like a light bulb or a light that's coming at me like this, and it may look like it's all the same kind of light. It's all white light. But actually the way that the light's hitting me is it's coming from lots of different directions. There could be lots of different colors that are coming from this light bulb to me. And so it's actually a big mix of light. When the light comes from that light bulb to me could be random. So in a way, when that light gets to me, it's actually kind of a random mess. Whereas the laser, everything's perfect. So you can start with one ray, you get two rays. Those two rays, you make a copy of them. Now you have four rays. You take those four rays, now you have eight rays, and they're perfectly identical in every way, shape, and form.
You were talking about different kinds of light. What makes laser light special?
One way to think about it might be to imagine, the air that's around us. So most of the time, we don't think anything about the air around us. You can ignore it. You could wave your hands around it. You could treat it as if nothing was there at all. But actually, there's tons of atoms all around us, and they're zipping around, actually moving quite fast, something like 1,000 miles an hour. And we don't feel things moving 1,000 miles an hour hitting us because all of the air that's surrounding us is random. The directions are random, the motion's random, it's hitting us at different times, so we don't really notice it that much. But now imagine that if I had all the air in the room, and instead of bouncing around randomly, it started to go more in one direction than another. We have wind. And so you can tell the difference from having some amount of directionality in the air that you didn't have before. And if you had all of the atoms, say, moving in exactly the same direction, then this would be stronger than any hurricane wind you'd ever have. And again, all these air molecules are moving around at 1,000 miles an hour, but they're normally running into other air molecules, and you don't actually feel that. But if you could just point all of them in the same direction, make perfect copies of them, then it would just knock you off your feet. And that's kind of the analog I like to think of with the laser. When we have something like a light bulb, we have like the air in the room, and so it's hitting you all kind of randomly. But if you have the laser, it's the same air, it's the same light, but it's all coming at the same time, and it's all with the same direction. And it's a lot easier to understand because now everything's moving the same way, so you can work with it in a way that you just couldn't imagine working with it before.
I know there are different kinds of lasers. I've heard of liquid-based ones and crystals. What are lasers made out of?
So you can make a laser out of almost anything, as long as a certain number of conditions are met. The material itself needs to want to produce the same kind of light that goes into it. And so different types of elements together will prefer to make different kinds of light. But the material itself really defines the colors of light. It wants to amplify. In many cases, you could have a laser out of a gas. So this might be a CO2 laser, or it could be a very common laser would be a helium neon laser, which is a gas that exists in a tube. And you can go ahead and use that as a laser. It's a very common laser that's used too. But some of the difficulties that we have, whether we use a gas or a liquid, is that they're kind of awkward substances to work with. If you have a gas, then you need to make sure it doesn't leak. Same thing with the liquid. So in a lot of more common places that you may see some lasers, we like to move things to solid state, something like a crystal, where we can manufacture them very nicely and precise, and they're just sit there. You don't need to worry about it leaking or doing anything like that. So these solid state lasers that are just maybe a block of glass or a block of crystal that we can just set there and manufactured to be exactly what we need, are kind of the easiest systems for us to work with for lasers.
There's a lot of different kinds of lasers in movies and TV. What are some of the ways you work with lasers in real life?
One of the most interesting aspects I find is that when the laser was created, we have this light and we know everything about it, and it's got this well-defined direction. And from a physics point of view, it's beautiful because we can write an equation and the light is doing everything in this equation. It's not even just an approximation. It really is what this equation is. So as a physicist, we love that, this perfect match between our math and the real world. But then it was thought of as a solution in search of a problem. It's like, great, so you write the math, what can you do with it? And this is actually what I think is kind of the power of basic research and understanding is once you really understand what the light can do and you can write this equation for it, then really your imagination is the only limit. And now, of course, we see lasers in all kinds of things. So we see lasers, at the supermarket where they can scan a QR code, but we also have technology where we have lasers that can go ahead and do surgery because you can focus light down tighter than you can with a scalpel. You can go ahead and use lasers for manufacturing. You can do welding in incredibly more precise and efficient ways that you couldn't do before. You can use lasers to see out into space. And so, for instance, we can focus the laser very high in the atmosphere to make it look like a star. And because we know exactly where it is and how we made it, it tells us what the atmosphere looks like to go through there to make that star. So now we can see into space better from Earth because we know what the atmosphere is doing. We can go ahead and put this in autonomous vehicles because now we know the light perfectly well. We can go ahead and see how far away everything is. And the list just keeps going on. Because once you have a foundational basis to be able to describe everything you're working with, you really can just apply it wherever you can.
Now, we have a laser pointer cat toy at home, and I've noticed it has classification information on the side of it. And I'm wondering if you could tell me, what does that mean and how are lasers classified?
This is a very interesting question. So one, there's, a safety level of classification that we use to describe lasers, whether you can hurt yourself with it. And then once you go up to a high enough level, whether you can hurt other people with it. And when you go up to a higher level, whether you can always hurt someone with it. And it turns out that's where the thresholding stops. And so you can have a laser pointer that meets the highest threshold. And then we can also have a laser that can go ahead and instigate fusion. And so both of those are the same category or classification of laser. But we can think of something like a laser pointer. This is maybe a laser that many people have seen. Certainly if they're seeing physics professors, they'd probably come across a laser pointer once or twice. And so this is a remarkable device, a laser that you can hold in your hand. It puts out very little energy in terms of the light that comes out of it. So we may have something like a 10-watt light bulb. This laser pointer will be putting out something maybe like 5 milliwatts. So 1,000 times less light that's coming out of this. So if I take this laser pointer and point it, even though it's such a small amount of energy and a small amount of power coming out of this thing, it looks very, very bright because all the light's coming out exactly the same way. So if I go back to the analog of the gas molecules in the room, I can ignore them even though they're moving 1,000 miles an hour. But if even a small fraction of them were all pointing in the same direction towards my face, I certainly would notice it. Same thing with this laser pointer. So now what's real interesting is that there's kind of two ways you can go ahead about making this laser more intense. One way is to add more and more energy to it. And so this means that as I'm holding my laser, it's putting more and more light energy out over time. And that's a knob you can only turn so much before you start needing a power plant to go ahead and provide that much light to come out of it. But there's actually another way to make this laser more intense, and that's by having a pulsed laser. Power is defined as a rate. It's how much energy you get per time. I might have a camera flash, and there's not going to be that much energy released, but it seems very bright because all the light was released very quickly. So if I am allowed to go back to this analog with the gas molecules one more time, if I had all the air molecules moving at 1,000 miles an hour towards my face, that would be pretty bad. But if all of them hit my face at exactly the same time, that would push me back way farther than if it were spread out over a long period of time. And that's a way of making this more intense, a more powerful laser, is if I take that same amount of light, but instead of slowly distributing that light over the course of something like a second, I pulse it. I deliver the same amount of light in a smaller period of time. So if I go back to this laser pointer, something like a 5 milliwatt laser pointer, and I take the energy in that, and now I deliver it in half the time, I've made it twice as powerful. And if I deliver it in 1/10 of the time, so 100 milliseconds, I've made it 10 times more powerful. So now instead of being a 5 milliwatt laser, it's a 50 milliwatt laser. And now I could think of what would happen if I took this 5 milliwatt laser light and instead of spreading it out over a second, I deliver it in a millionth of a billionth of a second. Then I would have a laser that is a million billion times more powerful than I started off with. The same energy, but so much more powerful and so much more intense. And these are the lasers that we like to use in my field, and the lasers that are the technology of chirp pulse amplification, which won the 2018 Nobel Prize, and what is the underlying technology for systems such as the NSF Zeus laser facility and the NSF Opal laser facility.
Speaking of those laser facilities, since the last time you joined us a year ago, you've carried out the first official experiment on the NSF Zeus laser. I know you haven't published results yet, but can you tell us a little bit about your experience with that?
Yeah, so we performed the first experiments at Zeus using their kind of flagship capabilities. So using the so-called petawatt peak powers. So this is turning Zeus up to 1,000 terawatts. And for comparison, a terawatt is roughly how much the US power grid is using at any given moment. And so if you can imagine harnessing the entire US power grid, multiplying it by a factor of 1,000, using that to do science experiments. That's what we're talking about here. And it only exists for a very, very, very short period of time, millionths of a billionth of a second. But the power is so high that you can really just make very extreme conditions that you wouldn't be able to see otherwise. And so in our first experiments that we've been able to perform out there, we're just shy of a petawatt. So I think the power that we were using was somewhere of the order of 800 terawatts or so. And when Zeus is fully ramped up, it will be 3,000 terawatts or 3 petawatts. These are very big numbers. And even so far, going up not even a factor of 10 in terms of the power, we've been able to go ahead and increase the amount of energy that we're seeing in the electron beams that we're producing go up by a factor of 10. So our accelerated electron beams were somewhere in the order of a few hundred MeV before. Now we've been able to see 2 to 3 GeV electron beams get produced from the interaction.
Now, what kind of applications can a powerful laser like Zeus be used for?
One of the applications that we can use Zeus for is to make a compact particle accelerator. So you might think of something like the big machine that we have over in Geneva, the CERN accelerator, and we use it to accelerate particles to very, very close to the speed of light. What we're looking at is ways of doing that with the light itself. So by focusing the light down, making a particle accelerator that instead of being something like 100 kilometers wide, we can make something that's on the order of centimeters. And so by using Zeus and using an accelerator that's basically the size of my thumb, we've been able to go ahead and make very energetic electron beams, kind of comparable to what you'd see with a couple kilometer machine with conventional technology.
You mentioned power factors, and I know you're a co-PI on NSF Opal. What is the goal of that project?
So in NSF Opal, there are 2 big things that are happening. One is we're pushing up that power another factor of 10. The NSF Zeus facility will be the most powerful laser in the United States at 3 petawatts. So this is 3 times 10 to the 15 or 3 million billion watts. Very high wattage there, very high power. This would be another factor of 10 more. So this is a laser that's 25 petawatts. Having that much power allows us to make the intensities go up higher to look at very new, interesting regimes that we just aren't able to access with less powerful lasers. But there's something else that we're aiming for with Opal as well. And that's, we've spent all of this time and effort making the most powerful laser. And at 25 petawatts, this will be the most powerful laser in the world. When we focus that light down, we can make incredible, extreme conditions that can make some of the highest energy electrons or do incredible studies in quantum electrodynamics and very high energy ion beams, incredible compact radiation sources. What would be excellent is if we can make a second Opal interact with those beams. Because if we think of the facility at CERN, what makes it interesting is that it collides the beams together. And so far, we've really been focusing on what we can do with one big laser. The unique aspect of Opal is that we'll have 2 of these beams that are able to make these very extreme conditions that can then interact with each other. And now we can look at events that we think only occur in some of the most extreme conditions of the universe. So very interesting laboratory astrophysics experiments that we've never been able to do on Earth before, we can now study. Different types of nuclear physics, different types of new particle acceleration schemes that we just aren't able to explore because all of the laser energy went into that one beam. And so there's just so many new opportunities that we can access by just being able to control not just where we put the light, but how we put that light in space and time relative to each other.
Special thanks to Franklin Dollar, Jeremiah Williams, and Slava Lukin. For the Discovery Files, I'm Nate Potker. You can watch video versions of these conversations on our YouTube channel by searching at NSF Science. Please subscribe wherever you get podcasts, and if you like our program, share with a friend and consider leaving a review. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.